Okay, so now we are live on YouTube, and let me share my screen. Okay, so today we're going to talk about more predicates, practice problem related to predicates, implications, and then we're also going to do some proof. There's a few announcements to start. First of all, the first homework is due this Friday at midnight. So make sure that is on your calendar. The most important part, which is in red, is that the next first quiz is next Tuesday, September 8th. And again, it's not going to be, so next Tuesday, we would not have a recitation. Instead, you can use potentially your recitation time to try to complete the quiz. It's going to be released between 7:30 and 4 p.m. And it's going to be released on Gradescope. So once you log into Gradescope, when you open it, you have 1 hour. And we built in a 15 minutes grace period after the 1 hour to make sure that you can upload your quiz over Gradescope. There's 2 review sessions. Actually, I should have edited. So next Monday, it's a holiday, but TA James, thanks James, has agreed to have additional TA office hour next Monday because our quiz is on Tuesday. So next Monday from 3 to 5, we have additional TA office hour, which we call a quiz 1 review session. And on Friday, actually, instead of written here, there's additional one from 10 a.m. to 12 noon with Zoe. We also, which is also on Friday, we have 3 TA office hour, which is also dedicated to review for quiz 1. So there's from 1 to 3, from 3 to 5, and from 10 to 12 noon on Friday. And Ilking is actually our newest TA for this class. So right now, this class has 7 TAs. The other very important part is for quiz 0. So we are going to release what we call quiz 0. It's a test quiz for Wednesday, tomorrow, and it's going to sort of duplicate exactly what would happen for quiz number 1 next Tuesday. So quiz 0 again is going to be released on Gradescope at 7:30 in the morning, and then Gradescope will close at 4 o'clock. Again, when you log in, you have exactly 1 hour to complete that quiz. But quiz 0 only have one single question. It's just to test your system, but try to go through that. So there is a detail over Canvas announcement about this. And then quiz 0 is not going to be graded, but it's just making sure you know how to use Gradescope to submit quiz on the day of the quiz. The most important part, there is a pledge page, which is basically you need to sign to say basically the only thing material I'm going to use during my quiz is this index card. And then there's a bunch of rules affiliated with the quiz. So the idea of you to go over quiz 0 is to make sure you know how Gradescope works and how to submit it. The important part is when you submit a quiz over Gradescope, you still need to match the page with outline. For example, if the quiz has, say, 10 questions, then you need to match, say, which page is my solution to question number 1, which page is my solution to question number 2. It's the same process in terms of matching the outline when you're submitting homework as well. For example, your homework, let's say, has 10, 12 questions. You need to match your submission in terms of page number against outline. All right, so this will be a good test for you to for the actual quiz itself. The important aspect on the day of your quiz is to make sure you set aside 1 hour time to do the quiz. And then once you start the clock, there's no pausing of the clock. You really need to have that 1 solid hour to really work on your quiz. Again, the suggestion is you can use potentially the time of your recitation to do that, or if you decide it's easy to do it early in the morning, that's fine too. But keep in mind, the submission is going to close at 4. For example, if you start at 2, you need to submit your quiz at 3. If you start at 3, you need to submit at 4. So the latest you have to start the quiz is at exactly 3 o'clock. Otherwise, you will not get all the 4 hours of it. Again, there's 15 minutes building. So essentially, you have roughly 75 minutes, but the last 15 minutes is reserved to help you submit. So don't wait until the end of 75 minutes to submit, because then the server will close. Okay, so 60 minutes dedicated to solve the quiz problem, 15 minutes dedicated to scanning photo and uploading to Gradescope. And one last thing, for quiz number 1, we built in a little bit fail-safe in case you have very major technical difficulty that you are not able to submit through Gradescope. There is an email address provided on the quiz where you can email a copy of your PDF to the TA, but only do not abuse this system. This is not for regular submission. This is when you have serious difficulty during submission. For that reason, it's very important for you to try out quiz number 0 to figure out how to work with Gradescope. Okay. So typically during the day of the quiz, there will be no recitation. So you have time to do your quiz. And for every exam, quiz 1 to quiz 5 and final, you are only allowed an index card, right? So the index card is basically roughly 8 by 5 by 11 piece of paper. You can use double side. When you submit, you need to submit a scanned version of your index card, so double-sided. So when you're doing submission, there's 3 things you need to submit for the quiz. Number 1 is your solution. Number 2 is a pledge. You need to sign that pledge. And number 3 is the index card. That, again, you need to match it against outline. Very important during exam, that the only resources that's allowed is your index card. You're not supposed to use any online resources. You cannot use your notes or your notebooks. It's essentially a closed book exam. Okay. So further, there has been some question regarding regrading policy. The syllabus has been updated. Again, if it's a regrading request for your homework or your quiz, you need to submit your regrading request through Gradescope within 1 week of receiving your score. However, with online, what we call the lecture problem set, because it's automatically graded by Canvas, so the regrading process is a little bit more involved, but here is what it is. Of course, read the syllabus carefully, but what we're saying here is that if you want to potentially consider a regrading for the problem set on Canvas, first of all, this happens very rarely. Majority of the cases when you think that why your solution is graded wrong is because there's a misunderstanding of the problem or your solution is indeed incorrect. So the first thing you are going to do is you go to Piazza. If it's a lecture 2 problem set, then you go under the folder under lecture 2. Do not post question for the problem set under quiz. Quiz 1, 2, 3, 4, 5 is actually for actual quiz questions. Okay, so for the problem set, go under lecture 2, for example. If it's lecture 2 problem set, lecture 3. If it's lecture 3 problem set, under Piazza, there's different folders. So you post a question there privately to the teaching staff. So in that case, both the instructor as well as the TA will be able to see your question. You say, hey, I have a question. I put this answer to my problem set, but it was graded wrong. I somehow believe my solution is correct. Here is the reason why. Okay, so you need to provide a justification why you think it should deserve a second look. And then the teaching staff will take a look at it. And then in most cases, actually, is a student has made a mistake. So in that case, you don't really need to request a regrading, because there's a mistake in your solution. But in some rare cases, which typically happen when you, for example, it's asking for a particular logic expression and you put extra parentheses in there. And in that case, that the Canvas grading would not be able to take care of those very rare scenarios. So if the TA decided is indeed a case that require regrading, then what we ask you to do is to, in the same folder, to send a formal request to which the title regrading request. Then a specific TA will go look at it and look at the discussion and then go correct your problem set points directly. So this has to be done in a manual process. But again, like I said, majority of the cases, it actually does not really require regrading. It's more of a clarification and Q&A for those problem set. Okay, so because we're going to have another quiz coming up, quiz number 1 coming up very soon, so you should try to utilize as much as possible the TA office hour as well as Piazza. Okay. And again, everything, the remaining of this slide is just to emphasize the only thing that is allowed for your quiz is the 8.5 by 11 index card. Okay.
We have a few questions in the chat.
Yes, go ahead.
All right, so the first one was about the homework assignments. Someone was wondering if they're able to compare answers with other students as long as they're not sharing the way that they found those solutions.
Okay, so I would suggest to read the syllabus very carefully. Syllabus has a very specific things about how to work in working groups. So the really idea about homeworks is you're supposed to write your solution independently. You're not supposed to. So let me just, if I do this, I can just actually share my screen about independent work.
Yeah, and I believe the student had already finished the assignment independently. Was just wondering about.
Yeah, the best guidance is to look at the syllabus. So for example, here, this is syllabus. Homework assignment are to be done independently. It is acceptable for students to discuss how to solve problem with classmates, but copying solution is considered academic misconduct. It's a student responsibility to ensure a successful and timely submission of each assignments and stuff like that. So, you want to make sure that you can discuss how to solve problems, but you should not be copying solutions. Does that make sense? So,
all right.
yeah.
So the next question was about having a calculator on the exam.
Yes, so we will be very specific. Right now, we don't allow a calculator unless it's specified in the exam itself. So we will make announcement whether for this particular exam calculator is allowed or not, and it's differ from quiz to quiz. For example, later on when we have quiz problem that is involving combinatorics and probability, depends on how we ask a particular question, a calculator may or may not be needed. For example, if I say, how many books, how many ways to choose books? If I choose 2 books out of 5 different textbooks, it's 5 choose 2. And then maybe instead of asking you for integer, we're just asking for a formula. And in that case, if you write out the combinatorial formula, that's fine. We wouldn't necessarily ask you for the final integer solution. But if we end up asking for integer solution where we deem it's necessary to have your calculator, we'll be specific about allowing or disallowing a calculator. So it's vary from quiz to quiz.
All right, and then the last one was, let's see, can my index card be digital where I write notes on it using my Wacom One drawing tablet? I'm an international student, and because of COVID, I don't have any paper with me now. So
okay.
The digital paper
So it's very important if you have an index card that is a
And just so you know, we can't hear you right now. Oh, let's see.
Sorry, my Zoom just crashed and I'm back. Sorry, I think I'm still streaming. Zoe, can you check on the YouTube channel to make sure we're still streaming? According here, I'm still streaming, but I just want to make sure it's going through correctly. Yeah, so what was the question? Would you repeat that question again? You are muted. Oh yeah, can my index card be digital? Yes, it can be. If you're using a digital index card, make sure that's the only thing you're looking at during the exam. Okay, you cannot use any other You cannot use any other sort of online browser, textbook, or anything. Just make sure that's the only thing you are accessing, right? Remember that internet is not allowed during the exam. You should not be using a browser to search for solutions and so on and so forth. You can have your laptop or your phone with that index card there during that exam. That's allowed. I know that not everybody have access to a printer at this moment. Another way to create your index card is to to write it down, to have a hard copy of index card, and when you submit, you can use you can take a photo, convert it to PDF, and submit. Oh, that's another thing. If you look at our Canvas page, we do have a few instructions of how to turn into a photo into a PDF. It's under the submission, homework submission page. So you should, again, for quiz number 0, if you are solving everything by hand, figure out how to turn your solution into a PDF to be submitted over Gradescope. Okay.
And it looks like we are still streaming on YouTube.
Okay, great. Thank you. All right, so now let's get started with a bunch of practice problems. I have to warn you that I have a bunch of questions that I put in the slides today, and we may or may not be able to go through every one of them, but we'll do as much as we can. And then for the remaining part, my suggestion is try to solve some of those problems at the end of the slides. Try to solve it on your own. And if you have trouble, figure out what the right solution is, please come to the office hour. Okay. All right. So let's start with the first one. This should be a problem that takes you roughly 2 minutes. And I'm going to give you roughly 1 minute of time to think about it. And then we're going to try to do this together, right? So this is just to say, I give you some English sentence with some variables. Can you convert the English statement using quantifiers and standard mathematical notations? By standard mathematical notation, I mean things we have learned so far using under propositional logic. Okay, one more thing to remind everybody, quiz number 1 is essentially on chapter 1 of the textbook. It's on number sequence and it's on proposition logic. Okay. So this thing here is x squared plus 1. This here is 2 to the power of n. Again, if this is, you are solving this on your own, think about what are the quantifiers that you have learned so far. There is for all, and then there is exists, right? So those are quantifiers we have learned in propositional logic. And then this is where they can become useful. And of course, there is also what is a symbol for integer and so on and so forth. Okay, so do we have a volunteer to tell me what is the first, what is the sort of the expression for the first question? You can type or you can raise your hand, and then you can unmute yourself.
All right, let me unmute you.
You can also unmute yourself if you are.
Okay, for number 1, I wrote the upside down A and then X.
Okay, that's for all. Yep.
Yeah, and then the E symbol for is in, and then the Z symbol for set of integers, and then comma, x squared plus 1 greater than 0.
Perfect. Yeah. So the first symbol is for all, right? For every, this symbol is for all. And then, you have a particular statement, which is x squared plus 1 is positive. Great, thank you. Okay, do I have a volunteer for the second one?
Okay, go ahead, Jake.
Yeah, so I said the upside down E, there exists n, or it exists within Z integer, comma, 2 to the n equals 32.
Okay, so you can pronounce this as there exists, right? So the first one is for all there's exists. So you say there exists an integer that belongs to this Z such that 2 to the power of n is equal to 32. Okay. So now the question, when we have made those statements, one of the question is, are those statements true or false, right? Let's look at the first statement is for all x that is integer, x squared plus 1 is positive, right? Bigger than 0. Is this true or this is false? Do we have a guess? You can type or you can raise your hand and unmute yourself.
Okay, in the chat, I'm seeing a lot of trues.
Okay. This is true because, if you think about an integer, the integer can be 0, positive, or negative. But if it's 0, 0 squared plus 1 is 1, it's bigger than 0. If it's different, if it's not equal to 0, then the square of the integer is bigger or equal to 1, and then plus 1 is also bigger to 0. So you go through sort of these cases to say this is true. If it's not true, let's find a counterexample, right? And then I can't find a counterexample, and later on we're going to go through a multiple proofs. You can actually prove that this statement is true, and then you're going to learn a lot of different proof techniques for this. The second question is now, is the second statement true or false? There exists an integer such that 2 to the power of n is equal to 32. Is this true or false?
Okay, true in the chat again.
There's a lot of true in the chat. This is true because what? Because there exists, if n is equal to, I guess 5, 2 to the power of 5 is equal to 32. So there does exist an integer that satisfies this condition. So the statement is true. Let's go over the next one. Okay, so now this is slightly more complicated, but not that too much, not too complicated. It's again, I have an English statement. You need to write out the logic expression and then compute the negation of it, and then decide whether the original one is true or the negation is true. Okay, so again, there's a one more step, but I will give you roughly a minute. All right, do I have a volunteer for the first one? Let's first translate the English sentence into my logic proposition in the mathematical notations, and then we're going to negate it. You can raise your hand and then, then you can unmute yourself. Or you can type the solution. I think typing is actually quite hard because it's mathematical formulations. But yeah, do I have a volunteer for this?
We do have a question. For number, do we use the real number R symbol?
So yes, so in here, let's say I'm going to assume it's, well, actually my problem didn't specify, but let's for the time being, let's say we can use this symbol. I think somebody raised their hand. Zoe.
So for number one, the negation.
For all x, yeah.
Oh yeah. So the negation, I think it's there exists an x.
So let's do the original statement first before you do the negation, right? Let's do the original statement.
Okay, for all x, that's between -2 and 2, comma. Squares. So I put 0 and then the less than sign, x squared less than sign 8.
Alternatively, you can also write this thing too. So this is a symbol. If you have not seen it before, later on you can use this symbol, which is belong to, right? It's an element of the set, but you can use this symbol right here, which is bigger or equal to. So now negation of the statement.
And then the negation, there exists an x that's between -2 and 2.
Yep.
Where x squared is less than 0 and x squared is greater than 8.
Is it and or is it or?
Or because the sign switches?
Yeah. So if you think about negation, right? Essentially negation of x squared bigger than 0, essentially and of x squared smaller than 8. If you take the negation, this would become x squared less than 0 or x squared bigger than 8, right?
Yeah.
There are a few questions in the chat about the bounds of this.
Yeah.
Should be using brackets or parentheses because the problem says it's between. Does that mean it includes -2 and 2?
Yeah. So in this case, let me be careful when I say between. I mean this means inclusion. It means it does include, but of course in the problems, in this case, since I didn't specify it, even if you use this, we probably will allow it. Just is an interpretation of, of this English word. But in the actual quiz, this will be one question. If you are confused, you can use Piazza during the exam to clarify this, okay? But here, when I mean between, I mean that inclusion, okay? All right, do I have a volunteer for the second part of the problem?
Sorry, there's more questions. What word would be used for exclusion? So if they were not being.
So actually for this particular class, we actually don't do, you mean X or?
Like if it didn't include -2 and 2.
Oh yeah, so there's a few things. You can say X is not in some set. This is belong and not belonging to. Is that the question? Or can you clarify the question one more time?
What would the question, so how it says for all number X that is between -2 and 2, and that indicates inclusion, what word would indicate exclusion?
For all number that is not between -2 and 2.
For, sorry. So if it was everything in between -2 and 2, but not including -2 and 2.
Oh yeah, we will be specified in English to say, I have a number between -2 and 2, but not including -2 and 2. We'll be very explicit with the language. Okay. All right. So let's do the second one. Do I have a volunteer? Let's do the original statement and then the negation.
So I don't have the negation yet, but my statement was there exists n inside negative integers such that 4n plus 2 is greater than 1.
Right. So of course, what is negative integer? Usually it's this symbol. It's the z integer with a minus on top. Okay, what is a negation then? We can do it together. I didn't copy it, but you can see what I mean by that. I can copy it. So what would be the negation? Remember when you negate existing symbol, it become for all symbol, right? So in this case, it's for all n belongs to negative thing, for n plus 2 is smaller or equal to 1. So when you negate an inequality, the direction switches. Okay? So now the question is, for the first statement, is the original statement true or the negation true? Let me rephrase it. Is the original statement true? I see some people typing or nodding head. So I'm assuming that the original statement is true, right? So it says that for any integer or any real number that is between -2 and 2, the square value is between 0 and 8, because the maximum value you can obtain in square is really 4 between this range. So yes, it's true. Of course, if this is true, then the negation is false. Okay. What about the next statement? It says there exists negative integer such that 4n plus 2 is bigger than 1. Is the original statement false or true?
People in the chat are saying the negation is true. And
So
then I've also got a question.
Yeah, so if the negation is true, then, so this is true, then the original thing is false, right? This is true, meaning that there exists a negative integer where 4 times negative integer plus 2 is smaller or equal to 1. One potential candidate of this is when n is equal to -1. So -4 plus 2 is less, of course, less or equal to 1. Okay, what is the question?
If you negate an inequality, does the inclusion of the equality always change?
Right, yes. So if you, for example, let me use a different color. If I have, say, x squared bigger or equal to 0, if I negate, it's not bigger or equal to 0, this becomes x squared smaller than 0. So the direction change, and then if the original thing has an inequality, then the negation does not include equality, okay?
All right, and then we've also got, as a general rule, if the negation is true, can the original not be true?
If the negation is, yes, so think about the opposite of true is false. So if your negation is true, then original statement is false, because a negation and the own statement cannot be both true at the same time. A statement and its negation cannot be true at the same time. Let's put it this way. And if negation is true, original thing is false. If original thing is true, then negation is false. Okay. All right, the next one is going to take you a little bit effort. That's why I put it into 5 minutes here. So this is a typical question you will get likely in the first quiz. This is try to prove logical equivalence. And usually it's asking for using theorem 2. And I'm going to start the clock right now. My major question for you is try to use the rules from the theorem 2. And here there's also the rule of precedence and the rule of substitution. And then also you need to use the property of implication. So let me give you a quick hint. Property of implication is that if I have P implies Q is logically equivalent to not Q implies not P. So this is something you will likely use for this, because this logical equivalence, when you want to prove the left-hand side equivalent to the right-hand side, you need to use the properties associated with implication. Okay. Again, you can prove from left to right. Precedence is a situation to say which logic operation takes a higher priority than the other logic operations.
And then there are a couple questions if theorem 2 will be included in the quiz or if it should be on a note card.
If we ask you to use theorem 2, then the theorem 2, like this table below here, we will try to include it in the quiz. but it doesn't hurt for you to also try to write in your index card because it actually helps review the material. But yeah, if we ask for it, it's going to be written on the exam as well. Okay, so one way to do this, you can prove from left to right, or you can prove from right to left. Typically, you can start from the left and then start using different rules. In this particular proof, you need to use the rule of precedence, substitution, and property of implications. Okay, so do I have a volunteer who has arrived at, okay, and also another way to prove, remember in this whole chapter, another way, if we don't specify to use theorem 2 and everything, you can also use a truth table. Okay, you can say, you know, you can have a column for P, a column for Q, a column for R, and then you have all the subsequent columns that uses those components, and you show that there is a column that corresponds to the left-hand side, a column corresponding to the right-hand side, and they agree among all the truths and false. So that's one way to prove. But here we ask you specifically to use a bunch of rules to prove it. So you need to do that instead. Okay. Do I have a volunteer? Okay, I have Jake raising the hand. Is Jake the one? Yeah, Jake, you can unmute yourself. Go ahead.
Yeah. I might be wrong, but I just took the contrapositive and because the equivalence, I mean, I might, is that a rule? Can you just take the contrapositive?
So here, this is the, you mean like contrapositive? You mean like this rule, the property of implication?
Yeah.
Yeah, okay. So that's fine, but remember, you don't want to skip steps. And using this property here in yellow, this is certainly an important rule to use to this proof, but there's a few rules that is going to pad it, and then we can go over that together. So essentially, you say at the core of your proof, you use this property, right?
Yeah, but I kind of just assumed that I could just jump straight to it. I didn't like pad it.
Okay. So let's do it step by step. You have the large direction correct, but we have to make sure we don't sort of, you know, lose some intermediate steps. For example, let's start from beginning, right? So the left-hand side is looking like this. So what I'm going to do is, first of all, I'm going to put some parentheses. This is what I mean by precedence, okay? So what that means is that I'm going to put parentheses over the operation that's going to be evaluated first. So in this case, I'm just putting parentheses between the hypothesis and conclusions. This is just me using what we call precedence. This is just to say that those operation that is enclosed by the parentheses is going to be evaluated first. Okay, nothing has changed. I haven't done anything. But the most important part, the second part, is using the property of implication. So this is P implies Q is equivalent to minus Q minus P. So this is based on the property, or you can just say property of implications. And now this is a case where I'm going to treat this as my big P over here, and this as my big Q over here. So I have P implies Q is logically equivalent to negation of Q implies negation of P. So if that's the case, I'm going to put negation over negation of R over negation of S. This implies negation of P and Q. So once you're here, you're not completely done yet. Actually, if you look at this, the next step you are going to try to write is actually De Morgan. So De Morgan is when you have negation on the outside. When you bring negation in, you switch the direction of the arrow, right? So the first term, I have to apply De Morgan to the first term, which is a hypothesis term. When I bring the negation in, double negation of R become R. but then the arrow has to switch from or to and negation of S become S. So that is the first term, right? So actually I can do, if I want to be very specific, I'm not going to skip any step. This is what we have. This is applying De Morgan's law on the first term. Now I'm going to apply it on the second term where I bring the negation in. So negation P, now and become or, that is negation Q. Now if you compare this, it's very close to my final conclusion, but I need to apply one more rule. And this rule is basically because I'm doing negation of R, this is the double negation rule. So if you look at this, this is double negation. And double negation is equal to the variable itself. So it became R, and double negation of S is S, implies. And because I have parentheses, I can get rid of the parentheses based on, again, precedence. So this became RS. I can get rid of the parentheses because I know which operation is priority. So the last step, sorry, round out the space, is precedence. Okay, so that's where we are for this question.
Okay, and then in the chat, do we lose points if we skip steps like precedence and double negation?
Okay, so it's important in this thing, we in actual grading will be a little bit flexible if you miss the precedence, because sometimes you use it without knowing it. You know that order of operation, which one comes first, which one comes next. But for this particular problem, the most important rule is, of course, the property of the implication, the De Morgan, and double negation. Double negation is actually an important step that you should not skip. And oftentimes, you also unconsciously will use a commutative and associative and try to remember when you're switching order, you're actually using those rules and try to keep as many rules as possible. But the most important rule for those is those three yellow parts. Those are the most important rule you're going to use for this particular problem. So I actually have more space here. I should have done it. So what I would suggest you to do is usually at the end of recitation, to go look at the pre-lecture slides and try, after you have gone through recitation, go back and try to solve the problem on your own. And then you can then go to the video and look at this solution here. Okay. All right, so if there's no more question, I want to do one more problem for proofs. And then there's tons of more problems later I want you to practice with anyway. So here is a simple proof, step by step. We're just going to go review it. The proposition is to try to show that for any rational number, I'm going to use the symbol Q. Any rational number R, the number R plus 1 is rational. So whenever we are looking at rational, hopefully this is covered in the video you watched, a rational number, if a number is rational, one of the property of being rational, or actually definition of being rational, is it can be expressed as an integer divided by another integer. So it can be expressed as a divided by b, where ab is equal to z. Okay, in order to prove this proposition, there's essentially 5 steps. The first step is to state the proposition in the mathematical term. So since Q is a representation of rational number, this statement become if R belongs to Q, then R plus 1 is in Q. This is the original proposition in mathematical term. And the next thing is now, if I want to focus on hypothesis, which is the first part of the statement, we want to look at what is a property associated with something being rational. Then it says, okay, then R is equal to A divided by B, where A and B are integer, okay? And the next one, which is really the key part of this, because in order for me to prove that R plus 1 is also a rational number, the idea is R plus 1 also fit the definition of a rational number, meaning that it's 2 integers divided by one another. So in this case, there's some algebra that comes into play. So in this case, I say I plus 1 is equal to A divided by B plus 1. This is just substitution. Substitute R by A divided by B. And then the next step is to express 1 by B divided by B, right? And then the next one is to sort of add the top part together and then replace the top part by C is equal to A plus B, okay? So the next step is to prove that now I have expressed r plus 1 is equal to a plus b divided by b, which is c divided by b, where c is a plus b. I need to prove that c, which is a plus b, is also an integer. And then this is an important rule you're going to use a lot of times in the proof, is there is certain operation over integer that satisfy the closure property. What closure property means is that integer is closed under addition, subtraction, and multiplication. What does that mean? If I have two integer, if I add two integer, it's still integer. If I subtract one integer from another, it's also integer. And if I multiply two integer together, it's still integer. So in this case, the c is an addition of two integers, so it's also by itself an integer. So now I have expressed r plus 1 as two integer divided by one another, which satisfies the definition of a rational number. Therefore, r plus 1 is a rational number. Okay, so that is the proof. Okay, so now we want to do this proof together. And I said 5 minutes, but actually, since we're running low on time, I'll give you 1 minute to think about this on high level of what you need to do if you're doing this. Okay, then we're going to, again, while you think about how to solve this, we're going to sort of follow this 5-step process. This first process is state the proposition. The second one is to study the properties of hypothesis. Last one, the third one is express conclusion. So when you say P implies Q, P is a hypothesis and Q is a conclusion. The third step is express the conclusion in terms of the hypothesis. Okay. And then the fourth step is to take care of details. And then the 5th step is to state the conclusion. So we're going to try to do that with this problem. Okay. So do I have a volunteer for the first step? If I were going to state this thing, what is my more mathematical notation? There's a, yeah, go ahead.
N modulo 2 equals 0. N plus 8 mod 2 is 0.
N mod 2, so equal to 0 implies n plus 8 mod 2 equal to 0. So there's various mathematical notation to do this. A number is even by definition is that it's divisible by 2. Or if you divide 2, it has a 0 remainder, right? So there's also another notation. You can also use this notation to be 0, or you can say 2 divide n. So n is divisible by 2. Those are other notation you can use, but let's use mod at the current notation, which is basically if I take remainder of it, there's a 0 remainder. Okay. So what is a property of the hypothesis? Here, right? One of the major part of this question is to understand what is the definition of even number mean. An even number, if it's even, it actually can be expressed as 2 multiply some integer, right? So this is the property of something be an even integer. So now for step 2, I need to make use of that. So I need to talk about the hypothesis, which is if something mod 2 is equal to 0, what does that mean? That means this number can be expressed by 2 times some integer, okay? So do I have a volunteer here? Okay, so let me rephrase it. So in here, I said it's an even number. So even number has a property. So it's if something is even, that means it can be expressed by 2 times p for some p that's integer, right? if an integer is even, then it can be expressed as 2 times some integer. That is the property associated with something being even. So the next step is now we have n is equal to 2p. Now I need to express n plus 8 in terms of the hypothesis. So now I'm going to use substitution. So n plus 8 is equal to 2p plus 8. Okay. So this is using substitution. And now I'm going to factor 2 out. So this is factor 2 out. I factor 2. So it's 2 times p plus 4. And then now I'm going to so this is the algebraic step. Now I need to take care of some details. Now I have to express n plus 8 to be 2 times something. Now I need to prove that 2 times something, that something is also an integer. So let q to be p plus 4. And then q is integer by closure. So that is integer is closed under addition. Okay? So because p is an integer, then p plus 4 is an integer. Q is equal to p plus 4, then q is integer. Therefore, n plus 8 is equal to 2 times q for some q that is integer. Therefore, which is the last step, n plus 1 is even. Okay? So we just go through this proof very gradually by going through all these 5 steps. But at the key point of this is to understand the definition of something being even. That is, something is even, by definition, is this number is equal to 2 times some integer for some integer. Okay?
And
So
then
yeah,
there is one question.
yeah, go ahead.
When we actually do the proof, do we need to write out substitution, factoring, closure, etc.?
Yes, yes. The key point of this proof here is you use a substitution, you use factoring, and then you use closure. Okay? But sometimes you may or may not need to specify the factoring, but then you need to specify there's a substitution. There's very importantly, there's a closure, because the closure take care of the detail, right? Why is p plus 4 integer? Because integer is closed under addition. So you have to say n plus 8 is now equal to 2 times some integer because of the closure property. Okay. All right. So so I'm going to start streaming.